Hello and welcome back to Psychology 301. This is Dr. Williams, and this is the second in the series of lectures over Unit 4A. This is 4A2. Last time we talked a little bit about stimulus control, and this time I'd like to focus on the processes associated with discrimination training. So discrimination training and discrimination in general, the ability to respond to different stimuli in different ways, can be studied in the laboratory so that we can understand the factors that influence how we learn to respond differently to different things, different stimuli in the environment. It's really scientifically important for us to understand this, and it's useful in an applied way for working with special populations. People with autism and other developmental disabilities or challenges often have difficulty with discrimination, so understanding how discrimination is affected by different factors allows us to tailor discrimination training for those individuals. It's also used in animal behavior and animal management. There are a number of zoos who use discrimination training for special husbandry work. So it's used out in the real world a lot. So let's talk a little bit about what's involved in training a discrimination. So there are two methods that can be used to train a discrimination. The first one is called single stimulus training, and it only uses an S+. It only uses a stimulus that signals reinforcement, and it doesn't use a S- or a stimulus that signals no reinforcement. It just uses that one single stimulus. The other method is called discrimination training, and it involves both an S+ that signals reinforcement and an S- that signals no reinforcement. So let's talk about the first one first, and then we'll go on to, so we'll talk about single stimulus training. All right, so the single stimulus training method, behavior is reinforced in the presence of just one stimulus, an S+. No S- is used. So you have the S+ stimulus. It could be a light for a pigeon or a tone for a rat. And whenever that stimulus comes on, if the animal responds, if the pigeon pecks, or if the rat presses a lever, they earn reinforcement. And they learn pretty quickly that pressing a lever or pecking at the light only works when the S+ is present. So they respond only when the light comes on or only when the tone comes on. So over time, that S+, that discriminative stimulus, gains control over their behavior. Testing, when we go in to test them, the trick here is to present them with all of the stimuli associated with that particular stimulus spectrum. So for a pigeon, we would present them with many different colored lights and see how they respond to them. With rats, we would present many different tones, high tones, low tones, and see how they respond to them. And what we find is that over time, the S+ gains control over behavior, but other stimuli also begin to control behaviors. So, and it produces a generalization gradient like the one that we saw in the last lecture by Gutman and Kalish. So here is that gradient that we saw before from Gutman and Kalish. Here we have, if you'll recall, that the S+ was 580 nanometers, which is a yellow key light for pigeons. And when they tested across all of the different wavelengths, what they found was that the highest rate of responding occurred above 580, which is the S+. But as you move away from yellow toward the yellow greens, the blue greens, and then down to the blues, you get less and less responding the further away from the S+ you move. The same is true on the other side. We start with yellow and we move through the yellow oranges and the oranges, and then out here toward the orange reds and the reds. And again, we see more responding for colors that are more closely related to yellow and less responding as we get further and further away from yellow. So this is what we talked about last time. This time I'd like to talk about the discrimination training method. In this case, the subject is presented with two stimuli. In the presence of the S plus, if the animal responds, they get reinforcement, but in the presence of the S minus, any responses are not reinforced. So the S plus in this case is green, they receive reinforcement, it tells them that reinforcement's available, and they respond. The S minus would be red, there's no reinforcement available. And over time, during training, the animals learn peck at green and they don't peck at red. And this procedure actually produces a peaked gradient, but it produces a behavior pattern that is very different from what you get with the single stimulus training method. So when you use discrimination training, you tend to see that the generalization gradients tend to be steeper. Single stimulus training, they're nice and round. With generalization training, they tend to be more pointed, and the responding to other stimuli drops off more precipitously. The subjects also tend not to peck at the extreme ends of the stimulus spectrum at all. You also get something called peak shift. And here the peak shift is where the peak in the gradient tends to occur in a spot that's not actually over the S plus. Instead, it appears to have shifted away from the S plus in the direction opposite the S minus, and it kind of looks like overcompensation. So let me show you what this looks like. Here we have two stimuli. 580 is yellow, so we're looking at green stimulus is the S plus at about 550 nanometers, and the more red or yellow S minus is no reinforcement. So here we have our two stimuli. Here's our SD and S delta. Now I'm sorry that this picture uses SD for S plus and S delta for S minus. This is acceptable too. This is both of them are common, but we tend to keep them together. So SD and S delta are the same as S plus and S minus. So here we have an S plus right here at about 550 nanometers, and the S minus or the S delta is here to the right, more in the direction of the yellows and the reds. And what we find when you look, there are two groups. One group has single stimulus training only. The other pigeon has discrimination training, and the single stimulus subject, the peak is right here above 550, and the discrimination group, the peak has shifted. Now the height of the peaks are different because they're different birds. One responds a lot and the other one responds a little. What we're really looking at is the shape of the curve, and both of them should, regardless of whether it's low or high, should have their peak above the S plus or the SD. But because of training with the S minus, we see that the peak in the discrimination training group has shifted. It shifted away from the S plus in the direction opposite the S minus. And so it looks kind of like they're overcompensating. It's kind of like they're looking at these different colors, and anything that comes up close to the S plus, and especially anything on the other side, gets suppressed, leaving the peak over here. It looks kind of like they're trying to avoid anything on that side of the color spectrum. So here is a study by Jenkins and Harrison in 1962, and they used tones with pigeons. And they trained three groups of pigeons. Group 1 got single stimulus training only. Group 2 got an S plus that was 1,000 cycles per second. That's the same stimulus used for Group 1. They both get S pluses, and it is 1,000 cycles per second, which is a tone. Beep. The S minus is 950 cycles per second, slightly lower, and they tested tonal frequencies for all of the groups. So in testing, after probably a week or more's training, they then went in and presented many tones to see whether or not the birds would peck at the light when the tone was on. And the results are that you get different kinds of patterns. You get a peak over the S plus for group 1 because it's single stimulus training only. You get a peak shift for group 2, and group 3 you get sort of a flat gradient. They're kind of the control group. So here's what it looks like. Here's the data. So here's our S plus right here, and the S minus is right below it. This is the 950 cycles per second S minus stimulus for that one group. And what you find is when you're trained only with, so the open squares with the dots is the single stimulus training only. So that's this one right here, the highest one, and its peak is directly over the 1000 cycles per second, right over that tone. And it tends to drop off as you move up and down the tonal dimension, okay? The second group with the dark boxes and the solid line is the discrimination group, and you'll see that the peak here has shifted away from the S plus in the direction opposite the S minus, so it's not on 1000 cycles per second, it's slightly to the right of 1000 cycles per second. And this little group here, this is the no training group. They get no discrimination training. They're just a control group, and they just respond at very low levels to all the stimuli relatively similarly. They treat them all the same. When the tones are on, they respond a little bit. But other than that, so here you see a peak over the S plus, a peak shift for the discrimination training group, exactly as we predicted would happen. Okay, so let's look at another study. This is a study by Hansen from 1959. This is a wavelength study. So again, this is colors on key lights with birds. They trained 3 groups of pigeons. In this case, they had 2 groups that received discrimination training, but their S minus stimuli were different. Our group 3, our control group, if you will, is a single stimulus training group only, so they only see 1 stimulus. All of the groups have 550 nanometers, a yellow key light, as the S plus. Group 3 has no S minus, and group 1 and 2 both have S minus stimuli, but with group 1, it's a red key light at 590 nanometers. For group 2, it's only slightly different from the S plus. It's an 555 nanometers, and so it's sort of yellow-orange. And they tested across all of the colors in extinction after about a week to 10 days of training. And we predict that group 3 will show a peak over the S plus because it's a single stimulus training only group. And because group 1 and 2 are discrimination training groups, we expect to see a peak shift for both of them. But the question is, which group shifted the most and why? So here's the results. And you'll notice that, so the black line here across the bottom, that's our control group peak over the S plus, just as we predicted. Both of the other groups have peaks to the left of the S plus because their S minus stimuli, the 555 and the 590, are on this side of the color spectrum, and over here we see that they so they shift in the direction opposite the S minus. However, the question is, which one moves the most? And hopefully you thought about this. You'll see that the 590 group, the one that's way over here, the 590 in red, shifts a little bit, but the 555 shifts even more. So we see a much bigger shift for the blue group than we do for the red group here. And that's actually a yellow light, not a blue light, but that's just the way the graph is. All right, so what we find here, is so group 1 shows a smaller peak shift, group 2 shows a larger peak shift. So remember, this is the one smaller peak shift for 590, larger peak shift for 555, and the question is why? And the answer is that the closer together the S plus and the S minus are, the harder they are to tell apart. So it's easy to tell that yellow and red are different, so they don't need to overcompensate as much. But when you have yellow and yellow-orange right next to each other, they really try to avoid anything at that end of the spectrum, and so you see a much bigger peak shift and these difficult discriminations produce more overcompensation. Okay. But of course, are they really overcompensating, or is there something else going on? Why is this happening? Well, one explanation for peak shift is that the critters are simply overcompensating, and that they're steering clear of anything that closely resembles the S minus. They want to stay as far away from the S minus as possible. Now that seems very intuitive. It's a good intuitive explanation, but it's not really very scientific, because what we're doing is we are making assumptions about what the pigeons are thinking. So in the late 1930s, Kenneth Spence proposed another theory to explain discrimination and peak shift. And he used the ideas of response competition and overlapping gradients that should be recognizable to you because they're similar to the ideas that underlie the dual process theory of habituation and inhibitory conditioning. So I'm going to stop there. Next time we're going to talk about discrimination, peak shift, and Kenneth Spence in particular. So have a nice day. All right, talk to you later.